So, hello guys. Today in this project, I developed an systematically refined regression module to predict medical insurance charges by using the structure of demographic and behavior data. So, while achieving a competitive Kaggle score was important, but my primary objective was methodological to understand how processing, feature engineering, and module complexity and the analysis tools interact in determine module performance and generalizability. So in this presentation, I will focus on two key questions to answer that. So first of all, which is what I did to improve the performance of my regressor. And the second one question is what I did to exercise and improve is a statistical fit. Okay, let's move on. Okay, for this slide, problem data size. So the data size contain 1,338 training observation and also have the 267 test observation. So the target variable is the medical insurance charges, which is continuous numerical variable. So this feature let's all include in these pages is age, BMI, and smoking status, and the number of children, and the region, and last one is the gender as well. So, the problem is the supervised regression task, where the goal is to predict future insurance costs based on the demographic and lifestyle information. And for this, is initial data exploration. So before I building any module, I just explore the data distribution, and totally I just noticed that a target variable, which is the insurance charges, is very highly red scored. So most of the individual have the moderate cost, but a small group of the individual have the extremely high cost, especially smokers. So this scaleness can negatively affect the regression module because the large value dominated the main squared arrow. And so that to addressing the scaleness become the important first step improving the module performance. And that's what I say. This page mainly talk about log transformation is which is improving performance. Like uh so to reduce the scaleness and stabilize variance, I just apply a log transformation to target variable using the log 1p. So the transformation compresses extremely value and makes the distribution more symmetric. So to training the module on a log scale improves the numerical stability and reduce the influence of the altair. Like after prediction, I just transform the output back to the original scale using the exponential function. So this was one of the most important step improving the module performance. Okay, so uh, to feature engineering to improving performance as well. So next, I just perform feature engineering based on the domain institution, and the smoking status has a strong interaction with both the BMI and the age. So for example, a smoker with the high BMI incurs significant higher cost compared to the non-smoker with a similar BMI. And therefore, I just create two interaction feature these pages, which is a BMI multiplied by smoker indicator, and the second one is the age multiplied by smoker indicator as well. So this engineer feature allow the module to capture the nonlinear relationship that may not be fully captured by original figures. So in addition, I just used the one hot encoding for the category variable such as the region and the gender. And for this slide, is module selection. So after pre-processing, I just experimentally with the several tree-based regression module. I tested 3 point. First of all is the gradient boosting regressor, and second one is the gradient boosting regressor, and the third one is a random forest. So the tree-based module are well suited for the tabular data and can capture nonlinear interaction without the manual feature scaling. So among these the modules, to a boosting-based method just consistently performed better than a linear module. And then is a cross like validation is very important. Is assessing to feed the module as well. So to assess the module performance reliable, I just use the five-fold cross validation. So the cross validation to help like, estimate how will module generalize to unseen data. So my cross validation mean squared error and log scale was approximately like 0.138. So with a relatively small standard deviation. So this indicates like the module performance is stable across the different fault. And now let's continue to talk about like learning curve analysis. So which is like diagnosing the fit. So in addition to crossing the validation, I apply to a learning curve to diagnose overfitting and underfitting. So initially, I observed like training error was much lower than the validation error and also indicating the overfitting. So which means that the module was fitting to the training data so too closely and not just generalized well. So after tuning like hyperparameters and reducing module complexity, the gap between the training and validation error is narrowed. So this like shows improved generalization and better module fit. And this part is talk like hyperparameter tuning, which is improving the performance and the fit as well. So to further improve the module, I just turned the several hyperparameters. So first, like I reduce the maximum tree depth to prevent overly complex trees. Second, I adjust the learning rate and the number of estimator to balance the bias and variance. So third, like I just introduced like regulation parameter and to penalize overly like aggressive split, and this adjustment just reduce overfitting when maintaining predicted power. So uh uh iterative like turning and validation, the module performance just become improve the stability. And for this part is a Kaggle result. When after do that, the notebook, I just submit to the CSV to the Kaggle website. So the first initially public score was probably like 87 million MSE, but it's not very good. But I think after the applying log transformation feature like engineering and also hyperparameter turning, I just improved my score to around 84 millions. So this demonstrate like the systematic module like to lead to the measurable like performance improvement. And finally, which is like the total final module, just show balance training and validation error. Like the validation variance is low and indicating a stable performance. So there's no several overfitting, and the learning curve suggests a reasonable generalization. So I just conclude that the module fits very appropriate like for the data set. And and so there's a key improvement like and summary for that. So I have like 5 points to do that to improve the performance. I think the first is the I apply the log transformation to the reduced guidelines. And the second one is I engineered like interaction feature to capture nonlinear effect. And the third one is I experimentally like with multiple module. And the fourth, I turn the hyperparameter systematically. And the last one is I just evaluate like performance by using the cross validation and the calculation for like feedback. And the final reflection, I just think like the project just demonstrate like the importance of combined data pre-processing and feature engineering like module selection. So like such as the cross validation and the learning curves. So rather than the relying on a single module, I iteratively I just refine the regressor. So totally like systematic improvement and careful assessment of the module fit, I achieved the stable and competitive performance. Thank you so much.